Hey everybody, welcome back. This is Mr. Piercy with your fourth lesson on differentiation. And what we're going to be looking at in this lesson is how you can kind of use differentiability to justify continuity with a function. And what we're going to be looking at first is we're going to try to show you when something is going to be differentiable and when it's not. And then we can try to look at utilizing differentiability to show when something is going to be continuous at a particular point. So this is what I have highlighted for you as far as that first bit of information. We're going to be focusing on how to determine when a function fails to have a derivative, because if it fails to have a derivative at a point, it cannot be continuous at that point. And in order for a function to be differentiable at a point, the graph must be continuous and smooth. And that's kind of a big deal right there. So maybe take your an extra highlighter or something and just really kind of underline this idea. They have to be continuous and smooth at that point. Now, in other lessons, we have seen things with where things weren't able to have kind of a tangent line at a point. And so that's kind of what we're going to be looking at first, is showing you when functions are not going to be differentiable at a point. So this is kind of what we're looking at for the definition of how you can show that something is going to be differentiable. Here a function f of x is differentiable at some value c if and only if, there's our biconditional statement from geometry, if and it's hard to see here, but this is the limit as x approaches c from the left side and the limit as x approaches c from the right side, they're going to be equal to some value, the same value, but here they're showing you that it's going to be some kind of a finite value. And you can see that they're looking at the alternate form of the limit definition of the derivative. So it will very easy. You should get numbers after you perform both difference quotients, regardless of what you're working with. You should get numbers on both of those. Now here, how f prime of a may fail to exist. What I have highlighted here is that a function will not be differentiable. It will fail to have a derivative at a point where there's a corner, a cusp, a vertical tangent line, or some kind of a discontinuity like a hole or a vertical asymptote, something along those lines. Now let's take a look at our first example with when something is not going to be differentiable. Now we've already seen something previous to this where it gave you, here we have just a function, an absolute value parent function that's been shifted to the right one space. And earlier on a previous lesson, you had something that looked just like this, where it asked you to draw lines that were going to be tangent to a point on the function, and one of those points was the vertex. A lot of kids have a tendency to want to say, okay, well, I'm going to have a tangent line here that'll have a slope of 0, and at the time we said, well, you can't have a tangent line there because the limit at that point doesn't exist. So if the limit doesn't exist at that point, we're not going to try to make it have something that's going to be that is differentiable at that point. Now looking here, we have the the absolute value parent function. I want to move it down here so I know I have enough room to write everything out. What is f prime of x? Meaning, what is the slope of the function as you approach one, and again it's hard to see, from the left-hand side, and this one will be from the right-hand side. Well, as we approach from the left-hand side, that is going to have a slope of a -1, and if I go from the right-hand side, you can see that's going to have a slope of a +1. So because the left and right side limits or derivatives don't match, the slopes of those don't match, that violates the differentiability at a point rule that we just looked at. So that's why it's not going to be differentiable. But is it continuous? At x is equal to 1? Absolutely it is. One of the things that we talk about for continuity is you can check it on a graph by just tracing it with your pencil. If you can trace the entire thing without having to pick up your pencil, it is continuous. So it is continuous at x is equal to 1, but it's not differentiable. And this is why. So here I'm going to say no, f of x isn't differentiable, is not differentiable at x equals 1, and the reason why is because the limit of the derivative that we had there, f prime of x, as we approached the 1 from the left-hand side, did not equal the limit of the derivative from the as we approach 1 from the right-hand side. So because the slopes of the f prime of x as we approached 1 and from the left and right sides had different values, a positive 1 and a negative 1, it's not differentiable, and that's just kind of reiterating the idea of that because I have that corner there, that absolute value is not differentiable at x is equal to 1. So moving on, we're going to take a look at the cube root parent function. And it's asking us to use the alternate form of the derivative to show that we're going to have a vertical tangent line. Now again, this is one that we've seen in the past where at our point of inflection you can kind of see as I approach 0 from the left, these slopes are kind of increasing, increasing, and increasing until they get to be vertical. And if I approach 0 from the left, they're decreasing, decreasing more until ultimately we have that vertical line. Okay, so why doesn't the limit here exist? Well, obviously the left and right side limits aren't going to have the same slope, so the derivative at that point isn't going to exist. So use the alternate form of the derivative to work this one out. So here, the alternate form of the derivative, so we'd say like f prime of x is equal to f of x minus f of a or f of c or whatever it happens to be. Here we'll say f of c because I have it noted that the input is going to be 0 in this case, and I'm using c. And so here this would just be x minus c. So f of x is going to just be the function, the cube root of x. Now f of c is when x is 0 or when c is 0. So here the cube root of 0 is 0. So that's your f of c. So we're going to have a 0 here and x minus 0 for c again. So now we're going to kind of simplify the numerator. I'm going to convert the radical into an exponent, so I'll have x to the 1/3 power over x. And the idea of converting it into an exponent is so that way we can use our properties of exponents. We have powers with the same base, so we can subtract those exponents. So that'll give me 1 over x to the 2/3 power, or 1 over the cube root of x squared, however you prefer to think of it. So show that the vertical tangent line, show that the function has a vertical tangent line at x is equal to 0. Okay, so we did the alternate form of the derivative, and we got these. Okay, so now we plug in 0 for that function, or for those expressions that we have. And so here I would say 1 over the cube root of 0 squared. Well, the cube root of 0 squared is still 0, so that is showing you that we have a vertical tangent line, something that is undefined when x is equal to 0. So here, let me just go ahead and add this. The limit is undefined when the tangent line is vertical. That didn't look like a very nice V, but vertical. So that's how we would use the alternate form of the derivative to show that we're going to wind up with a vertical tangent line as x approaches 0. And the next example is the reciprocal squared parent function moved 2 spaces to the left, and it's again kind of asking us to see, well, how can we show that we can't take the derivative at, in this case, something that's unbounded. We have our discontinuity where x is equal to a negative 2. So here, part A, describe the derivative of f as x approaches 0 from the left and from the right. So that's pretty easy. Here, describe the derivative of f as x approaches from the left or from the right. So the limit of the derivative of the function as we approach, what is it, a negative 2 from the left-hand side. Well, from a negative 2 from the left-hand side, you can see we're bending and we're heading up towards a positive infinity. And if I do the same thing from the right, the limit of the derivative as x approaches negative 2 from the right side, well, again, you can see as we approach negative 2 from the right side, we're bending and we're going up towards positive infinity again. Now, the left and right sides do go the same direction. They're giving us the same number, but remember, we don't have a limit at an unbounded region, which is what we're looking at here. So the slopes of those are undefined, so the function itself cannot be differentiable at x is equal to 2. So part B, given the derivative, so here this is the actual derivative of the function, and we haven't gone into the properties of derivatives yet, so we could definitely get this without having to use the limit definition of the derivative. But that is the derivative of the function that was given to you, and it's asking you to use that derivative to evaluate the function when x is a negative 2. So here we'd say f prime of negative 2 would be equal to negative 2 over negative 2 plus 2 plus 2 plus 2, there we go, cubed. And of course the denominator, negative 2 and a positive 2 is 0. 0 cubed is still 0. So I have negative 2 over 0, meaning that it is undefined, and supporting the idea of the vertical asymptote. Now here, this is a big idea for things that we're going to be looking at in calculus. Differentiability implies continuity. So that those two statements that we have there are very important. You need to make sure that you commit them to memory. If your function, if f is differentiable at some number x, or at some number c on the x-axis, then the function is also continuous at that point. So at that same value, if I can differentiate the function at some number on the x-axis, it must also be continuous, because you cannot have a differentiable function at a point if it's not continuous at that point also. So differentiability certainly implies continuity, but however, the flip of that doesn't hold true. That continuity does not imply differentiability. And we've seen plenty of problems, particularly the first one in this video with the absolute value that was continuous but was not differentiable at the point of continuity. Here, what we're going to be looking at, it says write the contrapositive of the statement. Now remember, a contrapositive goes back to conditional statements in geometry where you reverse the order of the hypothesis and conclusion, and you also negate them at the same time. So the conditional statement, P is the hypothesis, Q is the conclusion, so we'd say P implies Q. So the contrapositive would be not P implies not Q, or I said that backwards, not Q implies not P. So here we have the function the statement if a function is differentiable at x is equal to c. That's the hypothesis. Then the function is continuous at x is equal to c. There's the conclusion. So here I'll just kind of put this up here. This is the contrapositive. If a function is not continuous at x is equal to c, then a function is not differentiable at x is equal to c. And those are two true statements. The conditional statement is true, the contrapositive is true. This is what would allow us to write a definition as a biconditional form. So, but again, that's kind of reviewing stuff that we did in geometry. The conditional statements are things that you're going to see from time to time. So here, describe the x values at which the function is differentiable and justify your answers. Now looking at it, just looking at the graph, we should not be differentiable wherever we have a corner or a cusp. So looking at it straight away, right here and right here, I should not be differentiable. So I need to be able to find out, well, what are those values? Okay. So what I'm going to do is first, I'm going to take the expression of the absolute value, the x squared minus 5, and I'm going to find the solutions that one would give us as our quadratic, because we definitely have our quadratic piece in the middle, okay? But because we have an absolute value, none of our values can be negative, but the roots of the quadratic are going to come from finding its solutions here. So here I'm going to say x squared is equal to a positive 5. So that means that x would be equal to a positive and a negative square root of 5. Then if you take the square root of 5 on your calculator, positive or negative, you're going to wind up at those 2 points where we have the cusp on the function itself. So the function should be differentiable at every point except at positive or negative square root of 5. So here, describe the values. We're going to use interval. I'm going to use interval notation. So the function is differentiable from negative infinity up to negative radical 5. Now it's also differentiable between the negative radical 5 and the positive radical 5. And it's also differentiable from radical 5 to positive infinity. So those are the intervals that the function is differentiable at. It's only not differentiable at those two values, at positive, negative radical 5. And here, justify my answer. I can say that g of x isn't differentiable at x equals positive, negative radical 5. Since the function has corners there, and we could also kind of look at it graphically, or I'm sorry, not graphically, but we could look at it a little bit more from a calculus standpoint, because again, to imply that a function is going to be differentiable at a point, we have to be able to show that the limit of the derivative as x approaches, in this case, like radical 5 from the left-hand side, does not equal the derivative's limit as we approach radical 5 from the right-hand side. And this is kind of where I'm looking right here because I did the positive radical 5. And I could make a similar statement at the negative radical 5 and kind of show with the definition with differentiability at a point why it's not going to be differentiable. So now we are going to take a look here. Oh, nope, sorry. I feel like I missed something, but I didn't. Now we're going to take a look at some piecewise stuff. Piecewise functions are always a bit challenging to show differentiability because you have to ensure continuity at a point. And not only do you have to ensure that it's going to be continuous at a point, but it also has to be smooth at that point too, because corners aren't going to be differentiable. So here, what this is asking you to do, it says find all values of x for which the function is going to be differentiable. So what I have typed up there is it says basically find the values of x that make your function continuous. So this is how I'm going to kind of start looking at it. As here I'm going to show you that at x is equal to 0, because we do have to look at this two different ways. Oh, and I'm too far down. Let me scoot it up a little bit so we can see the whole function. There we go. So at x is equal to 0, we have to look at the domains of the function of the pieces. So we have to evaluate it at 0, and we'll have to evaluate it at 3. So at x is equal to 0, we can take the top piece, which is the x plus 1 squared, and we can set it equal to the middle piece, the 2x plus 1. Those two pieces should be equal to each other at 0 because they are going to come together. Their domains are going to interact at 0. Now, of course, 1 includes a 0 and 1 doesn't, but they're still going there. So we can plug in the value of 0 there. So here I'm going to say 0 plus 1 squared equals 2 times 0 plus 1. And so on the left side, 1 plus 0 is 0, or is 1, and 1 squared is 1. And on the right side, 2 times 0 plus 1 is 1. So the left and right sides at 0 match. They both give you a 1. So I'm also going to look at it at x is equal to 3. So at x is equal to 3, and we'll do the same thing. We'll say the 2x plus 1 piece must be equal to the 4 minus x squared component. And we'll kind of do our substitution. 2 times 3 plus 1 equals 4 minus 3 squared. And in this case, on the left side, we're going to get a 7, and on the right side, we're going to get a 1. And so 7 does not equal a 1. Okay? So at one point on the domains, we're going to have probably something that's continuous because we're able to show that the left and right sides are matching each other. But at another point, at x is equal to 3, it doesn't look like it's going to be continuous there. So what can we conclude about that? Well, what I can say here is that for the stuff on the left in blue, I can show that h of x is continuous along the interval from negative infinity up to the positive 3, when x is equal to 0. And the reason why, the limit of the function as, in this case, x approached 0 from the left side equaled the limit of the function as x approached 0 from the right side. Now, continuity doesn't necessarily imply differentiability, but is the function going to be differentiable at 0? It should be, because we're only looking at the quadratic that's there. If the quadratic itself is differentiable, we would just want to make sure that is the function smooth when it is when the quadratic as the first piece and the linear second piece kind of meet. Okay. So here, what we're looking at, the next thing I want to look at, and I'm still on the left side, what is h of 0? H of 0 in this case is going to be a 1, and that equals the limit of the function as you approach 0 from the left or the right hand side. So because the function is defined there and the limit is the same at the where it's defined, again the function is continuous, but I'm not sure if it's going to be differentiable because continuity does not guarantee differentiability. Okay, but if it's going to be differentiable, it's going to be differentiable here. Because as we see on the right, there must be a gap because the left and right sides don't give us the same value. So here I will go ahead and say that h of x is differentiable at x is equal to 0. So now let's take a look at the stuff on the right where the numbers didn't match. So here I'm going to look at it and I'm going to go, well, the limit of my function, not f of x, h of x, as x approached 3 from the left-hand side, in this case, did not equal the limit of the function as x approached 3 from the right-hand side. So the function itself, h of x, it's not going to be continuous at x is equal to 3 because the left and right sides didn't match on the limit, so the general limit doesn't exist. So if the general limit doesn't exist, it can't be equal to the function at that point. Remember how we have to satisfy the definition of continuity. Is not continuous at x is equal to 3. So my conclusion that I'm going to be looking at here is that, and let me do this in another color. My conclusion, let's do this in another color. That h of x must be continuous on the interval from negative infinity to positive 3, and then it would pick up its continuity from 3 to positive infinity, but at 3 itself it's not going to be continuous, and is differentiable and I shouldn't use the at symbol, at every point, and I'm running out of space, but x equals 3. So here I'm going to pause the video real quick so I can go to my calculator and see what this thing looks like on a calculator. So I encourage you to get your calculator out and try graphing along with this. So let's go ahead and I'm going to pause the video so we can see the graph of the function and go from there. Okay, so here is the piecewise function that we were just evaluating, and we're trying to see, okay, well, where is it differentiable at? And if you're looking here, we were evaluating it at 2 points. We were evaluating it at x is equal to 0 and x is equal to 3. Now, at x equals 3, Because the left and right side limits didn't match, we're clearly going to have a jump discontinuity here. And here, this is where x is equal to 7. That was the left-sided limit, and here x is equal to 1, the right-sided limit that we got. Now, the one thing that we want to pay attention to real quickly is we have to have it smooth here, and this really does appear to be smooth at 0. It looks like it's a very smooth transition between this quadratic piece and where the linear piece picks up in the middle. Okay, so this is definitely continuous at x is equal to 0, however, and definitely not continuous as x is equal to 1. So here, this is the one place we'd want to check to see is it differentiable at, because is it smooth, and it does appear that it's smooth. So I feel comfortable with the analysis that we had for that. So let's go back to the equation, to our notes here. And the next one here, I'm going to ask you guys this is where we're kind of getting in. This is what I was talking about for the piecewise functions. Here, piecewise functions can be difficult because not only do you have to ensure that they're continuous for differentiability, but they really need to be smooth, and that's something that can be a little difficult to do. So at this point here, I want you guys to go ahead and pause the video, and I want you to see, can you identify the values that A would need to be in order to make this particular function continuous over all real numbers. So pause the video, work it out, and when you're done, hit play and see how your stuff compares to mine. Okay, so here is the work that I'm producing to try and show the value of A, what it would need to be in order to make this particular piecewise function continuous. And here in a minute, I'm going to put up the graph to show you that I feel pretty comfortable that we got it continuous. So looking at the point where the domains overlap, being at x is equal to 3, we're going to set the two pieces of the equations, or the two pieces of the piecewise function equal to each other at that point, because that's where they overlap. So ax squared minus x is equal to 2a, and we do know the value at x that we're going to evaluate them at, so substitute the 3 in for the x's on the left side of the equation, giving me 9a minus 3 is equal to 2a. Getting a by itself gives us a is equal to a positive 3 over 7. So now we can kind of look at the left and the right side limits. So in the middle, I'm just putting my left and right side limits kind of equal to each other at the beginning, just to see, does the general limit exist. So x is equal to, so the limit as x approaches 3 from the left-hand side, we can take the 3/7 that we got and substitute that in for the value of a, and then we can just kind of do some direct substitution with the left-sided limit. So I can plug the 3 in for the x's, and I get ultimately 3/7 times 3 squared minus 3. And on the right side, that's just 6 over 7. We can't really plug anything in for x on that one because x isn't there. It's just a constant that we have now. And when I evaluate, I do get 27 over 7 minus 21 over 7. I'm just getting a common denominator on the left side to be equal to 6/7, and 21/7 minus, or 27 minus 21 over 7, that does simplify to be 6 over 7. So the limit exists. The limit as x approaches 3 should be a 6 over a 7. So the only other thing that I want to know is, to show that it's continuous, is the output at that point. Is when I say f of 3, do I also get a 6 over 7? And I do. Because of the continuous piece of the function, when x is equal to 3, y has no choice but to equal 6 over 7. So the limit of the function 6 over 7 equals f of 3, which is 6 over 7. So the function will be continuous across all real numbers as long as a is equal to 3 over 7. So here I'm going to pause the video for just a second so I can bring up my graphing calculator. And if you have your own graphing calculator, I would encourage you to graph this new piecewise function. So this would be the new piecewise function that we get substituting a in for the equations that or for our work. And so let me go ahead and pause and turn on the calculator. You guys graph it on your calculator also. Okay, so here is the function that I got. Now, of course, you can see here, this is the new piecewise function that we got, substituting the value of a into the piecewise function that was given to us. So 3/7 times x squared minus x across the domain, x is less than 3, and the constant 6/7 across the domain, x is greater than or equal to 1. And you can see we have the parabolic piece here coming down. And then here is the constant piece, and it's very clearly continuous now at that point. It's continuous at 3 as long as the a value was equal to 3/7. So I feel pretty comfortable again with the analysis that we did because the graph here kind of backs that up. Okay, so what we're going to be taking a look at here for this example, it's asking us to algebraically use the alternate form of the derivative to show why the piecewise function g of x is not going to be differentiable. Now, I think that the question got cut off a little bit. It's not going to be differentiable at 1. That's really what we're going to be looking at. So we have, this is the alternate form of the derivative, and so here, of course, I think we're looking at it at the number 1 because that's where the functions kind of overlap each other at. So let's take a look at the function here, and I'm going to say, in this case, the limit of g prime of x, this is what we're looking for now, as x approaches 1 from the left-hand side, because the left-hand side is going to be looking at this bit here, x squared is going to be what I substituted in for f of x, so I get x squared here. F of c, or f of a, or whatever you want to think of it as, is we're going to plug. So here, f of c, and that's not a very nice c, is equal to f of 1, and 1 squared is 1. So I'm going to say minus 1 here. And in the denominator, we're going to say x minus c, which, again, c is a 1 in this case. So in the numerator, we have the difference of 2 squares, so I'm going to factor that, x plus 1 times x minus 1, and the denominator has the factor of x minus 1. So the numerator and the denominator have a common factor of x minus 1 that will simplify, leaving me the function just x plus 1. And so now when I plug in the 1 from the left-hand side, we're just looking at 1 from the left-hand side, we'll just do direct substitution. 1 plus 1 gives me a limit of 2. So the slope of the derivative should be 2 when x is equal, as x approaches 1 from the left side of the function. So now we would look at the same thing from the right side. Well, the right side, as we approach 1, is going to give me this guy here. So here I'm going to say the limit of the derivative g of x as x approaches 1 from the right side, in this case, will be f of x is just x in this case. F of 1 in this case is going to be 1. And in the denominator, we're going to say x minus 1 again. And both of these, without even have to substitute any values here, x minus 1 over x minus 1, that simplifies to be a 1. So what we're looking at, what we're seeing in this case, is the limit of the derivative of the function as x approached 1 from the left-hand side, in this case, is not equaling the limit of the derivative as x approached 1 from the right-hand side. So in that case, this is why the function itself isn't going to be differentiable. Now let's look at it graphically, and I'll kind of go to my graphing calculator here in a second if you want to show you, or if you have your own graphing calculator, you can kind of look at it on your calculator. So we just have the linear or the quadratic parent function. So the vertex is here at 0, 0, and I have a point here at 1, 1, and then here at negative 1, 1, and then at negative 2 and 4. So if I try to draw the graph in, I'm going to kind of be overlapping some of my stuff here. So we just have something that looks like that for your function, for the quadratic piece anyway. And then for the linear piece, we're picking it up here, and we're basically having a line that goes this way. And it may not be exactly clear to you when I'm drawing it here by hand, but here I have a corner. And we established early on in this lesson that wherever we have a corner, we can't, the function is not going to be differentiable at that point. So that algebraically is why we're not going to be able to take the derivative of this particular piecewise function at x is equal to 1 because we have that corner. And now I'll just kind of jump over to the graphing calculator that I have, where you can see, I think you can see the corner a little bit better here on the actual graph. But you can see at x is equal to 1, there it's definitely going to be a corner. And so the derivative of this piece and the derivative of this piece, as we approach 1 from the left and right sides, algebraically we showed that those don't match, or those didn't match. So we're not going to have a ton left in this stuff, but unfortunately at the end we're going to be looking again at kind of some conditional statements that we're going to need to write out. Now here, this is kind of some things that we're going to be seeing on a calculator. Depending on the calculator that you have, the notes are giving you different instructions. So what you're looking at here on this slide is if you happen to have an Inspire calculator, you can kind of see either an 84, an 83, or an Inspire calculator. They're giving us the keystrokes to show us how we're going to be doing some derivatives on there. Okay, so what we see on the screen here, this is what it would be for like a TI-83 or a TI-84, one of the older looking graphing calculators. I believe most of us are probably going to have the Inspire calculators. That's what I'm using in class mostly. I'm going to try and do that stuff with you guys here. And here, they're kind of giving you the keystrokes. You would say menu, then hit the number 4, then hit the number 2, and then it's going to give you something that looks like this, and it's going to give you something that looks like this on your screen here. And I'm not sure you guys can see my cursor. I'm looking at my computer, and I can see my cursor going around, but I'm not sure it's showing up on the tablet that's actually recording things. But at the bottom, essentially what you'll see, that's what your calculator display would give you. Okay, and you can check it in both cases. The derivative of this quadratic equation or quadratic function as x approaches 3, in this case would return a value of 11. So let's just real quick jump to the graphing calculator. So let's go back here, and we're going to say menu calculus for 4, and then we're going to look at the derivative at a point. So our variable can be anything you want it to be, but usually we're going to say it's x. Well, what value do you want to evaluate it for? In this case, we're evaluating it for -3. And we're just looking at the first derivative, so we'll look at this thing here, and then we type in the function. We have x squared minus 5x, and then plus 6. And now we kind of have what it matches on the notes, and you hit enter, and we get the return of 11. So this 11, that -11, that's the value of the slope of the derivative of this function when x is equal to a -3. So here we would have a quadratic that would be graphed, and then at -3, the line tangent to the parabola at that point would be a -11. Now, what the idea of doing this stuff on a calculator is supposed to show you is that there's going to be some cases where the calculator will return things that shouldn't give you an answer. Okay? So here we just did that one, so we'll go ahead and pass this along. We're just showing you that you should get a -11 regardless of the calculator that you used. Now here, these are the functions that we started the lesson with, where we showed you a variety of ways that the functions are not going to be differentiable. For this absolute value, the function wasn't differentiable at 1. This cube root, because of that vertical tangent line, the function isn't differentiable at 0. And this one here, at the bottom, the radical function, or not radical, but the rational function, was not differentiable at x is equal to a -2. And what you're going to see here is that your calculator is going to give you something that's going to make it look like it might be, especially on the 84s. So let's take a look here. If you do what we just did by typing in this function using that math for 2, where you're just looking at the derivative at a point, you put x is equal to 1 and you type this function in there, your calculator is going to return a positive or a -1, which that's what we used to justify why the derivative wasn't possible at that point, because the left and right sides didn't match. And if you're on an 84, it's going to return the value of 0. So it's almost going to look like, you know, where that point was, where the vertex was, we are going to have a horizontal tangent line, but we're not. It's not differentiable at x is equal to 1. Okay? Here, the cube root function gave us the calculator. If you type this into your Inspire calculator, it's going to return something that says it's undefined, which is okay. But on the Inspire, when I did it on my Inspire, I got something that says 100. Okay, and the 100 is supposed to at least let you know that it's going to be vertical, that you have a tangent line, that you have a vertical line there. And the last one, the reciprocal function, or the 1 over x plus 2 squared function, on the Inspire, again, that's where at that -2 we should have had a vertical asymptote. So the Inspire is going to come back saying that the derivative is undefined at that point, but the 84 is also going to return a 0. And we know that's not right. So don't necessarily rely 100% on your calculator if you're trying to, you know, work through a problem that's giving you a hard time, and just accept the calculator at face value, because in some cases it's not going to give you the answer that you're expecting or that it should give you. So here, these are the last things that we're going to be looking at. Example 10 says, defending your answers. If you are given some function that's differentiable at x is equal to 3, explain why these statements below are going to be true. So we have these 4 statements here. Okay, and you can go ahead and pause the video and try writing these out. This is where we're kind of look at the conditional statements again. But here, if we have a function where f of 3 exists, then that means that function f is differentiable at x is equal to 3, or if f is differentiable at 3, then function f is continuous at 3. Well, if it's continuous at x is equal to 3, then f of 3 must exist. So according to the law of syllogism, what we see back in geometry is that if f is differentiable at x is equal to 3, then f of 3 must exist. So here, the limit of f of x exists as x approaches 3. So if f is differentiable at x is equal to 3, then it's continuous. If it's continuous at x is equal to 3, then the limit must exist. So therefore, again, using the law of syllogism, we're going to take the hypothesis of the first statement and the conclusion of the second statement and arrive at the conclusion that says, if f is differentiable at x is equal to 3, then the limit of function f must exist as you approach 3. So the next part, C, why is this statement going to be true? Well, here we have the alternate form or the alternate definition of the derivative. And what this is saying is that the derivative at x is equal to 3 exists. So if function f is differentiable at 3, then the derivative exists at 3. And that's essentially what the derivative alternate form is letting us know. And D at the bottom, that's the limit definition of the derivative. So here what I would be looking at is the limit definition is the derivative and says that the derivative of the function at x is equal to 3 exists. So if it is differentiable at x is equal to 3, then the derivative must exist at x is equal to 3. I promise there won't be a ton of these writing types of justifications with these conditional statements and laws of syllogisms and whatnot on your papers. But this is the logic behind these statements about how we're justifying that they're going to be true or not in some cases. But this is going to bring us to the end of our lesson 4. Again, man, I'm sorry about the length. I'm really trying not to talk so much, so I'm going to just shut up now. And thanks for watching, guys. If you have questions, let me know. In the meantime, take care, and we'll see you next time.